started. Let's continue our discussion from last time. We're still trying to talk about a Kalman filter. Last time we gave a very high-level preview of Kalman filter. I'm not sure how much you remember. So basically, Kalman filter definitely has been used extensively in various engineering fields, including control and robotics and many others. Okay. What I want you to remember is a few things only. Okay. First of all, Kalman filter, functionality-wise, in terms of its functionality, Kalman filter is the same as observer. Okay. If you look at the input and output of this block, Kalman filter does exactly the same thing as observer, including the Lundberg observer. Okay, it's trying to use system input-output data to give an estimate of the system state. The only difference is the following: is two major differences. One is the deterministic. Kalman filter does not adopt a simple deterministic model. They adopt a stochastic model. Okay, we will explain what this means later on. And also, it's not only give you a stable estimate, it gives you an optimal estimate of the state based on certain criteria. Okay, those are we're going to explain in more details. Okay, I also run over an example about a simple case. You can see that the Lundberg observer, if you didn't consider the noise that are intrinsic to the system model, then your estimator, your observer, will produce very large estimation error. But if you adopt Kalman filter, then your state estimate will be much more accurate. Okay, and we will learn how to do this. Another key thing I want you to remember, the first thing is that our Kalman filter is the same as observer. Okay, functionality-wise, it's the same as observer. It's just your algorithm is different. Okay. Secondly, in terms of algorithm, what I want to emphasize that Kalman filter is super simple. As I mentioned before, it just involves a few, maybe 10 or 15 lines of code, if you know what's going on. Okay, and inside the code, there's nothing but, I want you to remember this sentence. The Kalman filter is nothing but a recursive way to compute conditional expectation of the state. Okay, the state becomes a random variable now, and it's nothing but a recursive way to compute its conditional expectation. Okay, that's all. So, in order to truly understand Kalman filter, just memorizing a few lines of code or roughly the procedure, I don't think that will work. We have to truly understand everything about Kalman filter in order for you to be able to use it in the more kind of diverse scenarios. And so let me tell you a story. When I was, I think, a master student in the US before, that's maybe 15 years or 17, maybe, no, 20 years ago almost. All right. It's so funny. That's fine. Okay, I took a class called estimation theory. It's a graduate level class. Everybody told me that's really hard. And the instructor told us a little bit about Kalman filter at the end. And that's only for scalar case. Scalar, that's one-dimensional, and they teach you that with some kind of hand-waving discussion or proofs. And I asked the instructor, I want to know more. What's the general case of Kalman filter? Or how can I learn more theory about it? And he told me, even PhD cannot. We don't have the class, and it's take effort, it's really hard. Okay. Another student of is actually my friend, and they're in computer vision. You know, in computer vision, they have before deep learning time, okay? So if you want to do tracking, and you somehow use Kalman filter. So Kalman filter is well known in computer vision, Okay, if you search common filter tutorial, the most cited tutorial are from the computer image processing or computer vision the journals. Okay, so they use that, and the reason she can find a job in Qualcomm with very high salary at that time is because they were impressed when she did the intern there. She implemented common filter. They think, wow, it's really hard. Now I'm going to do ambitious goal. I want to make sure everyone in this room, as an undergraduate student, maybe junior or senior, you truly understand everything about common filter in the most general case. Okay, that's a challenge I'm trying to face. Okay, but I think you can. All right. The thing I need you to really be patient with me is that you have to go through the very basic building blocks for probability. So that's why today, maybe a little bit next time, we're going to learn or review probability. If you have very strong background in probability already, I think this will be a very kind of simple review for you. For many other people, this will be a good foundation that you need to pay attention to. Okay. As we discuss probability, it may sound a little bit too elementary. The thing I want to make sure is that you conceptually understand, because I realize most students, they have almost zero conceptual understanding, but they have 100% of manipulation skills of equations. Okay, if you see an exam, they know the equation, they copy the computer number, they even don't really know what the number is. Okay, how to test whether you understand something? If I randomly throw let's say this equation here, okay, I ask you to explain this one to someone else who didn't learn this class. If all you can do is read this, sk plus 1 equal to ask, b plus buk plus wk. So if all you can do is just read, that means you didn't understand. You just memorize it. Okay, you have to be able to speak out the meaning of the equations. So remember, when we do linear algebra, there are a few kind of things I repeat quite often, right? Linear combination, right? Linear combination of columns, things like that, right? So in probability, I'm going to do that as well. There are a few sentences I repeat many, many times. Okay, if you repeat with me, or if you memorize those sentences and try to understand them, that will become the best way for you to get into the conceptual understanding of probability of common filter. One thing I want to emphasize, as I mentioned, the common filter is nothing but computing conditional expectation. I think you have learned this before, right, Yuntian? Okay. By examples? Okay. Okay. How about other people? But I don't think you have a good understanding of what conditional expectation, even what conditional probability is. Okay. Okay. So this is very, very important. This is almost the most important thing. Conditional expectation, conditional distribution, conditional probability is the most important thing for many fields, including machine learning. Okay. In the sense that the review of me is basically trying to make sure you understand conditional probability and the conditional expectation. That's it. It's 2 words. So we have to start from the very beginning. Let me first ask a very simple but very high-level question. What is probability? Don't read my lecture notes. 你觉得呢？什么是 probability？ 你的自己的理解就行。到底什么是 probability？ What is probability？ Okay, she is a so-called frequencist. Okay, so 事件发生的数就是 the number of times the event occurs divided by the total number of occurrence of certain things. Okay, something like that. Okay, that's one way to specify probability. I think probability is what I wrote down here. It's a formal. You can have very kind of informal way, okay? A formal way to quantify uncertainty of our knowledge about the physical world. Okay, I have a very general question. Do you think the world, the physical world, is random or deterministic? 这个世界是随机的还是确定的？
Quantum perspective is deterministic. I think
Quantum, okay, quantum physics. According to quantum physics, this guy knows quantum physics, okay? According to quantum physics, he said that the world is deterministic. 小韩, what do you think? 你是确定的还是啊？你认为世界是确定的还是 probabilistic？ 小韩认为这个 he thinks the world is probabilistic. Any others? There's no right or wrong. The world is here. Your belief about the world is our personal view. Okay, my personal view is that majority of things we're dealing with is deterministic. It becomes random because of the lack of information. Let me repeat. The probability or randomness mostly because or due to lack of information. Okay? So let's say if I toss a die, longer side, okay, toss a die. And what's the probability of I see a 1? It's 6 numbers, right? Okay, what's the probability when I see it is a die? 1/6. Why you think it's 1/6? I think it's 0 because I saw it. It is not. It is 1 or 2 or 3. It's already determined, right? But it has a probability from your perspective. There's a probability. It's not completely determined because you don't see it, right? You can guess the likelihood it may occur. Okay. Well, I can give you another example. Do you think the stock market is probabilistic or deterministic?
probabilistic.
It's completely deterministic.
I think it's something called tails.
Let me tell you this way, okay? If you know everything about how many buyers are there, what are their offering price, okay? And how many sellers there, what's the selling price, and you know the computer program. Computer program is deterministic, it's written there, okay, to set up a price. You know all of this, then the price will be exactly predictable. The reason it's become random is you don't know other people's selling price, who will be selling at what time, okay? Lack of information is the primary reason something become random. Okay, to me, everything is deterministic. It's only about lack of information make something random. All right, that gives rise to a keyword I want to emphasize. I think that's really important for you to conceptually know probability. It's quantify the uncertainty of our own knowledge. It's your own knowledge. Your knowledge, your information is different from my information. So my probability will be completely different from your probability. All of the same thing. So there is no right or wrong probability, I would say. It's all about whether that reflect or truly reflect what you really believe. Okay, that's the key importance. Okay, so there's no complete right or wrong, it's your own belief. Okay, another thing that conceptual thing is when you say I want to define something probability, it's not like it always the number divided by total number of occurrence of something, and you have to follow some general framework or formalism, which is called probability space. Have you learned about probability space? Did you got introduced probability space? Okay, so if you want to formally define probability, you have to be able to specify the 3 key elements associated with probability space. Okay, one is sampling space. The other one is so-called event space, 世界空间，对吧？学过是吧？ Okay, the third one is probability. And probability is a mapping or assign each event to a number between 0 and 1, which denotes the likelihood of that event. Okay, let's give an example. Let's say we toss a coin. Okay, not a die anymore, a coin. You know a coin, right? What's the sampling space? Head or tail? Let's say tail is 1, tail is 0, head is 1. Okay, 0 or 1. Okay, that's the total what? So sampling space is the set of all possible outcomes. Okay, all the possible outcomes is either head or tail, either 1 or 0. Okay, what about the event space? You typically don't directly assign probability to outcomes. You assign probability to event. What the possible event space is all the possible outcomes, a subset of the sampling space. So it will be empty or 0 or 1. Is this each of these is a subset of omega, right? And also 0 and 1. Okay, total 4 possible events. Okay, so probability you can define probability for each of this event. Okay, I'm going to ask you, let me give a little bit more non-trivial example. Let's say I have tossed a die. Okay, then the sampling space will be 6, right? 1, 2, 3, 4, 5, 6. The number I'm going to see is this. Okay, then the event space will be still must contain empty subset and contain everything, which is 1, 2, all the way to 6. Let me do it from the smallest set to the largest. So that will be 1, 2, ... all the way to 6, right? And also 1, 2, 1, 3, ... Okay, keep going all the way to 1, 2, 3, 4, 5, 6. Okay, so you have a lot of combinations that are possible subset of the sampling space. So an event will be an element. An event A, let's say, belong to the event space. Could be, for example, A can be sometimes when you bet, you say this is a 2, 4, 6 means it's even numbers. Okay, you buy even, or you bet on even numbers. Possible, right? This is a element. This is the subset of omega. This is the element of F. Let me repeat. This is the subset of the sampling space, but it's an element of the event space. Okay, so then I'm going to ask you I can define probability. What's the probability of A happens? What do you think? You can define now, okay? That's your belief. What's your belief? What do you think is the probability of A? Huh? 1/2? You think it's 1/2, right? That's fine, right? That's possible. I may think it's 1/3. Am I wrong?
No, die.
It's up to me, okay? You cannot say this is wrong. This could be right as well. You have to understand this, okay? It could be right as well. It could be right because I see maybe the die has some geometry distribution so that it's more likely to show up the odd numbers than the even numbers. So my belief about even numbers will decrease. You never know what I know, right? So I think it's third. You cannot argue with me. Okay, it's my choice. Okay, if I know more, I definitely have a better choice. Okay, so there's no right or wrong thing. Okay, up to this point. So it's, I would say this number is completely up to the modeler. Okay, we're still doing modeling now. Okay, it's not, although it's not a state space model, it is a model to quantify uncertainty about your knowledge about the physical world. Okay, you got it? It has to be your belief. Okay. When you can say something is wrong, is you didn't follow the axioms of probability. Okay, so this number, I can assign whatever I believe, okay? But when I compose or compute probabilities, I have to follow some axioms. All the formulas you see in the later probabilities are all consequences of the axioms of probability. I think you must have learned this. Some people may choose different 3 axioms, okay, but we pick these 3, and because you know these 3, you can get to all the others. First one, probability of any event has to be bigger than 0. Probability of a whole sampling space is 1. This one is important. Okay, A intersect B is empty. That means they are the so-called disjoint. Okay, they don't really intersect. Their intersection is 0. If for disjoint sets, the union of their probability has to be the probability, the sum of the probability of the individual event. Okay, I think those are you must be very familiar with, and you should be able to derive almost everything from these 3 axioms. Let's do an exercise. What do you think of this one? Probability of the empty set is 0. It's not from the axiom, but you can, if I, by the way, I can change these 2, by the way. Anyway, so given this axiom, I can derive this, right? The reason is probability of the entire sampling space equal to probability of entire sampling space union empty set, of course. And these 2 are disjoint. So by the 3rd axiom, I can say this is equal to this. But I know this guy is 1 by the 2nd axiom. So, and I also know this guy has to be bigger or equal to 0. Everyone, right? So this, sorry, I know this guy is 1, and I also know this has to be bigger or equal to 0. So I can claim that empty is 0. Okay, I can derive this. That's showcase. This, I think you know this, but I think you should start from axioms. That's the very roots of almost all the consequences. Okay. Another important thing we are going to use quite a bit is the so-called law of total probability. You have learned all of this. I'm just recalling this and with my own kind of perspective. So if you want to, let's say you have a, let's give an example, okay? If you have a entire sampling space, you may have a partition of the space in the sense that I have A1, A2. I can partition this into two disjoint set. The set has to be disjoint, otherwise it's not a partition. Okay. Now, if I want to compute a set, the probability event B, what I can do is I can say probability of B equal to probability B intersect A1 plus probability B intersect A2. Okay, it's nothing but from this graphics, it's this part and this part summing up together. Okay, and you can prove this because I don't want to prove everything, okay? Otherwise, we will not move to anywhere. It's because this guy is probability of B intersect, intersect what? A1 union A2. Okay, intersect, this guy is the whole omega, right? So that's why, and these two are disjointed, and you can make the sum become the sum of these two terms. All right, so this is a law of total probability, and why this is important? Because that allows us to do divide and conquer. I'm going to use this term quite a bit. If sometimes it's hard for you to directly specify a probability, okay? But you know, under this case, it is something. Under that case, it's another thing. It's called divide and conquer. So you divide the computation of B into some simple cases, and you sum them together. Any questions? All right, now let's move on to the next one, which I'm going to challenge you a little bit. So the so-called conditional probability. Can anyone explain what's your knowledge about conditional probability?
New probability.
It's a new probability.
Much different from the
Probability is, well, that's true. Everything he said is correct. Okay, that's right. Any other understanding? 郭金德，你说呢？先验和后验 ，prior and posterior. Okay. Okay. Yes. 一件事情 so one event occurred, and okay. So as I mentioned, the probability or the randomness come from what? Information. Okay. If information changes, the uncertainty will change. You have to modify the probability measure. Okay. So before, nothing happened, but now an event occurred, then the probability measure has to be redefined because your knowledge, everything else has been changed. Okay, I think all of you know this formula. I don't want to repeat this formula. So conditional probability, the probability of A given B is probability A intersect B divided by B. I can only read this. That means I didn't explain much to you, right? So now I'm going to explain a little bit more about what this formula really is. And you have to pay attention, okay? What does it mean? I think somehow I missed one. From the notes, I missed one slide. This will be my page 9. This is 10, right? And this is 8. Okay, I missed one slide. I'm going to write, okay? So, conditional probability, first of all, the key word here is not, it's conditional is used to describe this probability. By nature, conditional probability is a probability. Okay, sounds trivial statement, but you should understand conditional probability is a probability, so it has to have its own probability space. Okay, the sampling space, the event space, and the probability measure. Okay, given the original, let's say given original, let me write below, okay? Let's say we start with a probability space, okay, with its omega, f, and p. That describes our knowledge about the whole uncertainty evolved into this possible outcome. Let's say this is my omega. Okay, I'll assign probabilities to each event inside F. Now what happens is, the first one is, now let's say event B occurred. Event B occurred. Okay, event B occurred. So probability space will change it, right? So probability space will change it. New space, new probability, or new space. If I want to write very, very rigorously, I should use different notations here. Okay, omega. What do you think is omega tilde now? You may never even think this way. Okay, that's the way you should think. All right. So this is the event. Now I say, okay, this is my B. Okay, this is my B. B occurred means it's hard for you to think abstractly. If you think about this as omega, this is our toss a die example, for example, okay? Then B may be our even, okay? You see an even number as an outcome, all right? So after you say, so some guy tell you, okay, if you are playing this, okay? Someone toss a die, and someone see the true outcome and tell you, okay, it is an even number. That's almost like a hint. Okay, that's a hint. It's still random, right? You still don't know which even number it is. Okay, so now what is the total? What's the outcome? What's the new probability, or sorry, sampling space? Now, all possible outcomes is B. B is a set, okay? Outcome is a set, all right? So in other words, i.e., omega tilde is B. So your total possible outcome become B. Outside B, it is not a possible outcome anymore. Suppose the information is true, all right? Okay, omega tilde becomes B. And what about F changes as well, right? Right. So for example, if A belongs to F, that means A is a subset of F. Now, yeah, A is a subset of omega. Now, A may not belong to tilde. You see what I mean? So it's not a subset of the current space. For example, I can say A is small, means that 1, 2, 3. That could be A, right? All right. So A, according to the new probability space, it is not a subset of the new sampling space, by the way. Okay, but A intersect B belong to this. Okay. In other words, now you want to evaluate. Let's say this is my A. Okay. I know some part of A is impossible. Okay. Only this part has meaning. Only the other part, this part has some meaning, right? So that's A intersect with B. So F tutor actually contains, so F tutor should contains all possible, so contains subset, all subsets of omega tutor, all right? A intersect B is a subset of omega tutor. Okay. Well, now we don't have to specify completely about tutor. All we care is really how to compute the number probability, right? So defining omega and F is help us to kind of formalize the things, avoid avoid making some mistakes. What about how do you specify the probability? I can specify it any way I want. Okay, I can specify any way I want, but one thing is that we want to be consistent with the original P. Okay, it's not because everything all of a sudden changes. It's just one thing happened. It's just one event occurred. The metric, I want the original metric to still be able to guide us to determine this P tutor. For example, I would say, suppose C, yes.我好像 reset 了。Okay, works. 可以吧 Okay. Okay, now suppose C is a subset of B. Are you with me? C is a subset of B, so C must be a element of F tutor now, okay? C is somewhere, let's say this is a C, this is a C. Okay, originally C is a subset of B. What do you think I should assign probability of C?
Why C is an element of F tutoring?
Because the subset of B.
Is it B an element of F?
Yes. No, this is the new omega tutor, right?
Oh, yes.
So C is a subset of omega tutor, and F contains all the subset of omega tutor, so C must be in F tutor. So probability of C tutor, what do you think? Can I say this is just, I can use my previous probability. Is that okay? You can specify any way you want, by the way. Is this a valid thing? No, right? If you define this way, then that's wrong. Then probability of this will become probability of B less than 1. Okay, it violates the axioms of probability. What we should do is that just a possible, okay, it's not only one. I want to emphasize. Deformity regard is just one possible way to determine conditional probability that we always use. A possible way is we normalize it by dividing B. Can you see the difference? These are the original probability measure, and this is the new probability measure. Okay, in this way, I will say probability tutor of omega tutor would be P of B divided by P of B is 1, right? It satisfies, because now B occurred. So the probability of B, the conditional probability of B given B occurred has to be 1. Okay, so you have to normalize it. Make sure this is 1. Okay, So if A is not a subset of B, right? If A is not a subset of B, then we can only compute, after we see B happens, so we can only compute A, probability of A, as probability of A intersect B divided by B. The only this part has some randomness, right? Only this part has some randomness. And I can only evaluate that randomness dominated by that, okay? And I will define this guy as using the same notation, but they're different, right? This P is different from P tilde. So I want to say PA is not original PA given B. So this is nothing but a new measure. The conditional probability formula you saw before is a way to conveniently use the original probability measure to define the new probability measure after an event occurred. Okay, I may not. Okay, that's all I can do. You can think that requires some time for you to truly understand. I don't see any other people talk about this in the way I talk. That's how I understand it. I think roughly correct. Okay. Okay. So you have to understand one thing. If you don't want to follow everything I said today, one thing you have to keep in mind: conditional probability is a probability. Okay. And according to this formula, that's the way that's to use the original probability measure to define the new probability after you see a event occur. Let's use an example. Let's jump over to a slide. Let's directly see an example. Conditional probability. This is very simple. A bowl contains 10 chips of equal size. 5 red, 3 white, and 2 blue. We draw a chip at random and define the event. A is the draw of a red or a blue chip. You understand the question? What's the event A is that you have 10 chips, okay? You have 10 chips, 5 red, 3 white, and 2 blue, okay? You random pick one. A is the event that you pick a red or blue, okay? And now suppose you are told that the chip drawn is not blue. The dealer tell you, okay, I can give you a hint, it's not blue. This event occurred. What's the new probability of A? Okay, let's see, that's a conditional probability problem. That's the most simple one. First of all, I want you to know or go through the formal steps. You don't have to go through formal steps for every question you see, okay? But for now, for us to somehow get started with a little bit more abstract way to understand probability, it's better for us to start from the basics. Can you tell me what's the sampling space? The original probability space, okay? What's the sampling space, Omega? Let's call it right 1, right 2, right 5. There's 5 right, 3 white, white 1, white 3, white B1, B2. What does each of this mean? This is all the possible outcomes, okay? You can either see a red, the first red, the second red, or you see a white, or you see a blue, okay? What about the event A? It's not blue, okay, then that's 5, R1, R2, R5, and W1, W2, W3. Oh, event A is a red or a blue, sorry. So that's 2 blues. B1, B2. Okay. What about B? It's not blue, so that will be R1, R2, all the way to R5. It's not blue, so W1, W2, W3. That's B. You have to be able to kind of convert a problem that described to you as a real-world examples to some mathematical formalism. So I'll ask you, what's the probability of A? This probability is what? It's the original probability before you are told about B occurred, okay? So that will be, suppose everything is the same, equal size, right? So you pick them complete random. So what's the, will be 1, 2, 3, 4, 7 possible case divided by 10, all right? That's the probability of A. What about probability of B? 8 over 10, which is 5, so 4 over 5. Now I will ask you, if you are told B occurred, that means what? Some part in A is not possible, okay? You have to update your probability. So the probability will not be probability of B anymore. It will be a new probability tutor of B. So typically we'll write like a probability of B given A. Okay? Let me be more formal. Sorry, I don't use this word. Actually, this is the P of this P. Okay? That's my P. And this is a P tutor, which is new probability measure after you see B occurred. Sorry. Probability of A. After you see B occurred, that's a new probability measure. I define like this. By the definition we introduced from last slide, we know this is A intersect B divided by P of B. Why you need to divide it? Because now the entire B is everything you live in, right? It's the whole sampling space. You have to scale it so that its probability will be 1, okay? So that will be A intersect B is what? 5. Are you with me? A intersect B is all these 5s. So so probability A intersect B is 5 over 10. This is 4 over 5. Overall, we have 5 over 3.
5 over 8. It's impossible to.
Oh, sorry. 8. I'm writing wrong, okay? 8. It's impossible to be larger than 1, of course. Okay, that's conditional probability. It's elementary, right? And it's just like I introduced in linear algebra. I start from the very basics and gradually speed up. So we'll do the same thing here. Okay, let's take a break.